Hello, everyone. Welcome to the Permafrost Network Seminar Series 2024. So today, Rae would be presenting her research work. So Rae did her honors BSc in Environmental Sciences with specialization in geochemistry and exotoxicology from University of Ottawa. During her undergraduate degree, she had the opportunity to volunteer in Cryospheric Research Group, which allowed her to develop an interest in the Northern Arctic research. Rae is a recent graduate of Carleton University with MSc in Geography. Her research is on legacy drilling waste sites in Western Canadian Arctic, a project that was built in collaboration with the Inuvialuit Regional Corporation and Inuvialuit Land Administration. Now I hand over to Rae for her research work that she would be presenting.
Hello and good afternoon, everyone. So like Usman said, my research is on the integrity of drilling waste sumps in the Mackenzie Delta area of the Northwest Territories. And I just finished my master's thesis this past semester, so finally done and getting to present all of the results to you today. So starting off with what is a sump? So sumps are these large pits that were dug in permafrost in order to contain different types of waste. And the ones that I'm interested in contain drilling fluids that were used during oil and gas exploration. In order to facilitate drilling within permafrost regions, we need drilling fluids that go into the borehole to facilitate drilling. This provides the borehole with stability, in addition to allowing for any sort of cuttings to come out with the fluids itself. And so drilling in somewhere like Ottawa, you could just use water and it would function pretty well for you. But where we have permafrost, you need to ensure that these fluids don't freeze when they're interacting with freezing ground temperatures. And so what's done to these fluids is a whole bunch of additives are added, including potassium chloride, which is a freezing point depressant. And in most of these fluids, it was added up to 10% by weight per volume into the fluid. So quite a bit of salt has been added into them in order to lower the freezing point to about -8 degrees Celsius in most cases. And why we're concerned with the state of sumps and sumps in the region is due to climate change. So these were built under the assumption that permafrost would act to contain the fluids in place and freeze them in place indefinitely, but with warming ground temperatures and deepening active layers, the stability of these sites has become compromised. And so when sumps were built, the idea was to blast the ground and excavate all the material out, creating a pit that's about 5 meters deep, putting the fluids inside in order to freeze them in place, and then those excavated materials being put on top as the sump cap. And the idea behind the sump cap was to create this domed structure which would contain the active layer, so that way the permafrost would act to contain the drilling fluids in place. And why sumps are such a concern to us is because it's not an issue of just one or two of these things, but over 220 in the Mackenzie Delta region itself, and over 1,500 in the territory, which is quite a number of sites. They're on average about 100 meters wide by about 80 meters in length, and they're all throughout the region. And so for my master's research, I studied sites in 2 different locations to be able to compare different terrain types. And so I was looking at sumps that were both in the delta itself, which is where we're going to have warmer ground temperature, occasional flooding, different sediment types as well, and compare that with sumps that are present in the upland, which is typically colder permafrost conditions and not experiencing that flooding. And so what a sump actually looks like, not in an idealized diagram, is this. So this sort of square-like shape found throughout the landscape. And here at Naglintac B19, we can see one of the channels of the Mackenzie River right over here. And the presence of driftwood on the site indicates to us that some flooding has occurred. And so the objectives of my research, and the objectives of studying sumps in this way are to assess the location of the drilling fluids and in the sumps themselves and see how that's changed over time. And so we're really lucky in the sense that we have past surveys that we can compare with the surveys that we did in 2022, and that allows us to see how these sites are changing over time and assess if they're containing the fluids or if the fluids themselves are dispersing into the environment, as well as examine factors that may be associated with increased fluid distribution into the environment, and seeing really if there's differences between the performance of sumps that are present in the uplands, so in that colder permafrost, with sumps that are in the delta, which is a warmer permafrost region. And so one of the ways that we're able to analyze these sites is using an electromagnetic conductivity probe, or an EM31 for short. And how an EM31 works is that you get this long machine that Tim's carrying is the EM itself, and it sends a conductivity signal into the ground, and essentially it's completing a circuit where the drilling fluids are present. So where we have that conductive saline fluid, we get a reading, and therefore we're interpreting it as the presence of drilling fluid. And where we don't get any sort of high readings or we get zeros, we're assuming that that is permafrost or frozen ground underneath us. And that's one of the ways that we can map out the ground conductivity, which helps us to better understand the presence of these fluids within the environment. And so Tim carried this heavy machine along this path. And so each point that you see on this map right here is where one measurement is taken. So it's taken at a depth of about 5 meters, and it takes multiple measurements and just averages it for the whole piece. And so we're able to take these maps of ground conductivity measurements and analyze them further. And so I'm going to be going through a case of that here at the Malik site, which is pretty unique because here we have 3 drilling mud sumps that are of different ages within the same environmental conditions. So we're able to better compare and assess if there's something else contributing to the stability of these sites or instability. And so we're able to take the readings that we get in that dot map and turn them into contours. And so here we're actually able to compare that with past surveys and present conditions. And so in 2012, we see these beautiful concentric circles going up to an elevated point of conductivity near the center of the sump cap. And this is the 345L38 sump that you just saw in the previous slide. And this is the 2L38 sump. And we're, again, getting that concentric pattern of elevated conductivities moving towards the center of the sump cap, versus background concentrations are elevated in some regions, but they're not as high. Versus when we look at a survey a decade later, we see this elevated conductivity again in the center of the sump cap, but then we're noticing a decrease in the conductivity in the surrounding terrain. And then at the 2L38 sump, we're seeing a decrease overall in the conductivity on the sump cap. One thing to note about this site is due to its proximity to the Beaufort Sea, we do get quite a bit of flooding, which is why we're seeing these elevated conductivity readings right over here. And then the last sump at this site is the L38, which was built in the 70s. And this sump, its concentrations are quite similar to what we're seeing in what we consider undisturbed terrain. And so this is a great way that we're able to compare what sites looked like about a decade prior with current conditions to assess where fluids may be in the environment. And why we're happy to see those concentric circles is actually due to the solute redistribution that occurs during freezing. So these drilling fluids or drilling muds were made with a whole bunch of different additives. And in an ideal world, it was all suspended in solution as one sort of homogeneous solution. And over time, as we get freezing within sumps, which is freezing in a closed system, because we're getting freezing from the permafrost all sides in, freezing from cold air temperatures. So that frozen piece goes along the outside, so the ice starts to form on all edges to start. And ice is really finicky, as it doesn't like to accommodate random pieces in its crystal lattice structure. And so anything that isn't pure water or isn't forming as ice gets pushed into the center. And so we get this redistribution of solids right into the center of the sump cap, which is what we were seeing here on both of these sites in 2012 and more noticeably in 2022. The 345 L38 sump was the only one that had it. And that would indicate to us that the drilling fluids are present within the center of the sump cap. And looking at sump performance more broadly in other locations, this is one of the Parsons Lake sites. And its previous survey only had a small subset of information, which is why you'll see this gray area surrounding it. And it's also present in the uplands of the region, so in those colder permafrost conditions. And here we're seeing in this earlier survey that we're getting higher levels of conductivity recorded with the EM. And then about a decade and a half later, these measurements have decreased slightly, but they still have decreased. And another way that we look at the data on and off of sumps is by separating out that point map of ground conductivity into the readings that we're getting on the sump cap itself and in the undisturbed terrain. And then we can take those data points and put them into different software in order to see the distributions of the measurements. And so doing that and creating this box plot, we're able to see that the sites that were built in the 1970s have low conductivity both on the sump cap and in the undisturbed terrain, and that's pretty consistent across the board, except at the SICU C55 site, where there were very few measurements that were able to be taken on the sump cap because about 75% of it had been ponded, which is likely influencing the measurements and the readings that we're getting here. Versus at Nuna I-30, there's only a small pond adjacent to the sump cap and only extending into a small portion of it, but we're getting this much larger distribution of measurements and much higher readings. And when we actually go and look at the survey, we're able to see this area of elevated conductivity right in the center of the sump cap, which is what we would be expecting. And this is the camp sump that wasn't analyzed, but essentially it just has like human waste in it. So the sump that we're more focused on is the one with the drilling fluids present, where we're getting these concentric areas of elevated conductivity. And so we can do this sort of distribution experiment for the sumps that are in the delta as well. And when we look at it, we notice overall all of the sumps, both in the cap and the undisturbed terrain, generally have higher conductivity readings for all of it in comparison to what we see in the uplands. And this is likely due to an increased water content at these sites and flooding during storm surges, which may influence and import some other conductive materials. And so we're able to see here that, again, the sites that are built in the 1970s have a very similar distribution of measurements on the sump cap and in the undisturbed terrain across all sites. However, the youngest of the sumps, built in the 2000s, experience an elevated conductivity signal on the cap in comparison to the undisturbed terrain, except for at F29, where we see a very similar conductivity signature on the cap and in the undisturbed terrain. And when we look at the conductivity and contour line map of it, we're able to see this sort of advective pathway of migration out of the sump. And this corroborates some reports that were put out in 2007 and in 2009, which indicated that there was a potential migration pathway extending out of the sump. And they've had to go back in and regrade the sump and add more materials onto the cap. It's had a number of issues. And so our surveys help to corroborate this information. Another way that we're able to look at these sites is by using inductively coupled plasma mass spectroscopy, or ICP-MS for short. So soil samples and water samples were collected across the site at the ponds and in a T-transect in order to get a better understanding of the elemental composition at the site, so determining if the drilling fluids were present and in sort of what concentrations we're looking at. So in order to analyze the soil samples, the pore water was extracted, which sounds like an easy process, but took a little bit of creative thinking to do. So we ended up with two different centrifuge tubes. And so the first one, we cut the bottom off of it and it acted as just a little cup. And then the second tube, we cut the top off of it to shorten the tube and added a hole in the bottom. And this allowed us to fill the first longer tube with soil and put the cap at the bottom within the larger tubes of the centrifuge here. And after using the centrifuge and spinning it around for about between half an hour and an hour, the pore water from the soil sample was extracted into this little cup, and then that was prepared for the ICP-MS analysis. And the results of our analyses, again, we're able to compare the data that we collected on the sump cap with the undisturbed terrain, and overall, all of the elements of interest, so sodium from sodium chloride, which was what we would get from seawater, especially at those sites where we're getting occasional flooding, especially during storm surges, as well as potassium from potassium chloride, which is that primary freezing point depressant added into the fluids. We're able to look at all of these elements and see that for all of the sites in the delta, these elements of interest were seen in much greater concentrations on the sump caps than in the undisturbed terrain. And we saw similar results with what we see in the uplands, although this sort of nice, simple summary graphic was not able to be made for the sites in the uplands because some of the caps themselves were completely ponded, so we didn't have samples for them, as well as because it's in a drier region, some of the soil samples didn't produce enough pore water to be able to be analyzed. And so that caused a number of issues with data comparison for the uplands, which is why we don't have that summary graphic. Another way that we're able to visually see how sumps are performing in the region is through aerial surveys. And so this helps to, by taking photos in aerial surveys over time, we're able to see subsidence of the cap and also how pond and water dynamics have changed within the environment. And so in 2009, this photo was taken by Steve Coquel doing some work out in the Delta. And both of these sites are Niglintack B19. And we're able to see here that there's two distinguished ponds from one another within the region. And then just over a decade later, these ponds form a sort of megapond and have completely expanded. And so we're able to see visually these changes in time. And of the 12 sites that I analyzed, only 4 of them had ponds covering less than 10% of the sump cap, and two sumps had ponds covering over 75% of the sump cap. And why we're so concerned about ponds is due to the thermal influence of them, especially the sumps that have over 50% of their cap ponded. Those ponds end up going quite deep, and that if all the water can't freeze during the winter, then you can't actually get ice forming on top of the sump. And so it acts to keep the sump warm even during the winter time, which can cause further degradation of permafrost beneath, as well as thickening of the active layer. And so this is one of the sumps where we see about 95% of the cap has been completely ponded, although there is little visual difference between the photo that was taken in the early 2000s with what was taken in 2022, essentially it has completely subsided and been infilled. And so what this actually means for the state of sumps in the region is that we're seeing higher conductivity values in the soil of the delta, and that's because of the flooding that occurs within those sites. So especially during storm surges, bringing Beaufort seawater onto the sites, causing those elevated readings. However, we're also seeing at those delta sites that there is an elevated region of conductivity, typically within the center of the sump cap, and that's from the ICPMS data. And when we're looking at generally the performance of sumps, both in the delta and in the uplands, we can say that it's similar in the sense that some sites are performing as intended versus other sites are not performing as intended, and indicating that there could be some migration of the fluids or that the sites have failed. And what this really means is that there's other factors at play, and it's not just an environmental thing. You can't say that just the sites in the delta are failing or just the sites in the uplands are failing, but rather there's something else contributing to their performance. And what we were able to find within our work has been that age plays a huge factor into how a sump is performing. Especially those sumps that were built in the 1970s appear to have dispersion of fluid, versus younger sumps tend to be performing at a level that we would expect for their age and tend to be doing better than the sumps that were built in the 1970s. And all of this work would not be possible without so many people helping with reviewing documents, field plans, brainstorming, providing funding. So thank you to all of the collaborators and communicators and everybody who's helped out on this work.
Thank you very much, Rae. If anybody has any questions, more than welcome.
I can't remember exactly which slide it was on, just so I can understand it correctly. I think it was before when you had the distributed soils where you had the red dots sort of dispersed and then concentrated. And there's a slide just before that one. You know, a recent survey and then a historical survey. The scales, the dimensions of those areas are roughly the same. So the boxes are roughly the same scale. And like on the left-hand side versus the right-hand side, there are changes in the contours. And is that also just the measurement resolution or the way in which it's plotted, or these are actually indicative of the degree of that change?
Yeah, so starting off with this 2012 survey, it's actually from a report, and
Okay.
it's all in color. And so in order to have it be comparable with the data that we have and have it be consistent across the 12 sites, it was made into contours by hand, which is why it may not be to the same sort of resolution here. Although during my defense, there was a couple of discussion points that came up of how I processed the data. So I went from point data to a tin to a raster, and then made the contours from that. And had data processing been a little bit different, perhaps these contours may have been smoother, but that's knowledge I have now and I didn't have at the time of making them, which is why they look a bit more choppy and angular than maybe people would expect.
Okay. Yeah, no, I don't have any expectation. It was just the visual contrast was what piqued my interest. So thanks.
Rae, I just had a quick question. So it's regarding these surveys that you have done. I believe that the time of the year would have a significant impact on what you're measuring and what was measured in back in 2012. So how do you, what are your uh, thoughts about it? And did you do at around the same time of the year? And was the weather being compared as a parameter?
So weather wasn't compared as a parameter, but we did try to make sure that all of the surveys that we had direct comparisons for were done during the same months. So usually August, late summer conditions is when these surveys had been done. And there's only one site, which I didn't show here today, Glyntac B19. Its previous survey was done in late April, so under late winter conditions. However, those changes are like noted and explained throughout my thesis. But here today, all of the sites that were compared, the surveys were done in the same months, just different years.
Okay. Thanks.
Hi, Rae. This is Olivier Pirot. Congratulations for your research. I have a general comment. I know I saw my name actually in your presentation.
Yeah.
I've worked on the Malik site on the client side, right, for years. And a general comment for this research, but for others, is not to be shy to reach out to industries, for example, or just like myself, right? And see if you can get access to some of that data. Because most likely, that there would have been an opportunity to share some more data about Malik, for example. You saw through the open file that we wrote with Michel Cote and others, right? There's a lot of data, but site photos, for example, right? We've been to that site every year for over a decade. EM surveys are most likely, the JPEG, the Japanese folks on the project. I don't think they would have objected for you to have the raw data file. So it's just something to keep in mind when doing some work in the ISR, right? To reach out to some of the owners of those sump, and I think for them it only make good figures to show that they're contributing to science, and I'm pretty sure they would be willing to share some data.
Yeah, so another part, not directly on my thesis, but an adjacent piece that I've been working on for the past 3 years is I sit on the Sumps Technical Working Group, which is a contribution of industry, academics, Inuvialuit, and territorial government. And we've tried to get some data sharing with the other sites. I have a number of sites from ConocoPhillips itself, and so there is definitely some issues with requests for data that were not answered. And so I think that definitely played a part into me being a little shy to reach out to more people to ask for data when those roadblocks had been hit. But definitely a really good point of like, there is a lot of people working in this field and definitely always more room for collaboration and meeting with folks to hear what they've done.
Yeah, and I can agree with that. So I think we need just to be insistent on our request. But again, congratulations.
Thank you.
And sorry, maybe one last comment. You compare older sump performance versus recent sumps. I've looked. I'm looking, I guess, currently at some of the more recent sumps, early 2000s on the delta, but not just on the lower delta, but also on I guess the upper delta or Richardson's Islands, for example, or upland terrain, right? And I have multiple examples where you do have those upland sumps that are also failing. So the low-lying terrain, obviously the storm surge is a key contributor, but we do also observe the degradation process on some recent sumps.
Yeah, definitely. And I think for our work, that was just kind of like a main piece that popped out. And I think the Malik site is a really great example because you have 3 sumps of different ages, so you can make those comparisons. But yeah, there's sites that definitely appear to be performing as intended and a number of sites that experience some issues. And I think it just warrants further investigation. And I know there's like a lot of programs now that are being built up to look at sumps and to investigate things further. So definitely a lot more work to be done.
Yeah, I agree. Thanks.
Thank you very much, Rae, for your awesome presentation. And I thank you everyone for making yourself available for the seminar.